Hi all. Today we will understand what are the challenges in making LLM outputs deterministic. As you understand, what is a deterministic output? The deterministic output is basically whenever you run the same query or a same input to any given function, if the output is repeatable and the same, then it is called deterministic behavior. So, if you are asking an LLM a prompt, and if the LLM with all the same given settings gives you a same result, then it is called a deterministic LLM, or else it is called non-deterministic LLMs. So we will today see what are the challenges that are making LLMs to be non-deterministic as on today. Just to note, most of the findings are inspired by this particular blog post, which is from Thinking Machines, defeating the non-determinism in LLM inference. So many of the people who try to read that blog were thinking this is, the non-determinism problem is solved and LLM inferencing is now deterministic and all. But we will see what are the challenges, what are the prime two direct challenges, and what are the indirect challenges with the LLM inference to come up to a deterministic output. So that's what is this video for. Uh, there is another language version, Telugu version is also there, which will be released on Thursday. So if you are Telugu native speaker, I think I would recommend you to listen to that session as well. So let's get into the problem of the day. Okay. What is the problem statement? Okay. When, let us suppose I go to any image creation algorithm and ask, create an image of a red apple in studio lighting. So let's suppose I asked this particular question to an LLM. So every time you ask this question, for the point of a discussion, let us keep uh, so that we are using the same machine, same endpoint, and everything other is the same. Then, even if you keep every other parameters the same, when you ask this question, most probably you will come up with this kind of a answer. Why do you think, or why this kind of a things happen? So the entire discussion of this video runs around the reasons that lead to this kind of a problem. So, if you want to understand why this kind of a problem is first uh, experienced, okay, you need to understand how your LLMs work. Okay, so basically, if you see any LLM in the world, okay, if you start with giving it a prompt. Okay, when you give a prompt is a set of tokens or a string of a tokens essentially that will be fed to an algorithm. So when the prompt is fed or a string of a tokens are fed to the algorithm, what it will do is in the first step, it will split it into tokens, and there each technical token or each language token is given a vector embeddings. Okay, so now these embeddings are the real world uh, understanding of the language for a LLM or a machine. Okay, now these embeddings are multiplied with the context. There are many techniques which are there: self attention, multiple attention, different attention techniques. And for the interest of the black boxness of LLM, because this is not the main topic, we will keep it's a black box, and there are some multiplication with the algorithm that goes inside the intermediate matrix. So what is the output of a LLM? Whenever you do these matpulse and everything, at the last moment you will get logits. So what is the logit is when you complete a sentence or ask a question, LLM will always give you the next token. So the next token prediction will always be at a point where you give a logit. So logits are basically the probabilistic multiple options of the next token, and which token is very much near to the expected output. Based on your settings, the next token is picked up. So now this is how an LLM works. This is at a very high level I'm trying to explain. When this is happening, all the matrix multiplications which are going behind, they happen using the floating points. Okay. So now what is a floating point? We all know floating point is a representation mechanism inside the computers which will be able to represent non-binary and fractional items. So that's what a floating point does. It's a primary context or primary data type of the any computing platform. So now when these floating points are generated and the logits are coming out, the last softmax function will actually pick up the exact output of your LLM. So this is how an LLM works. So now if there is a problem in the floating point calculation itself, then you are back to square one. That means your logits will be modified. This is the reason. This is the core reason. Floating points itself being non-deterministic is the core reason for non-deterministic behavior of the LLMs itself. So, having said that, let us see how floating points are not non-deterministic. So we are going one level down to understand why a floating point calculation for a LLM is not non-deterministic, how why it cannot be repeatable. So that is where we are going there. When it comes to floating point inaccuracies, there are two problems with the floating point inaccuracies. One, the rounding of errors and the calculation errors itself in each of the atomic operation or each of the step. That the second problem is floating point associativity problem. Okay, what is associativity? Most of us already know what is a associativity problem. Where in mathematics, in real mathematics, if you take a pen and a paper and account for all the continuous digits of a floating point multiplication, most of your floating points are associative in nature. So there is no real floating point associativity problem in the real world mathematics. But then when you come to the computers, this problem is always there. Okay. So why only computers have a associativity problem? We will see in this video why it is there. So uh, what happens here is like a plus b plus c is not equal to a plus b plus c. So when you add a, B, and C, three operands, and you add A and B first, and then you add C to it, is not mathematically equal to adding B and C first and then adding A. In real world mathematics, it will not be the case. In computer based mathematics, this is the case in most of the times. Why? Let's take an example and understand the real reason why this kind of a situations happen. Do you see this example? Good. So, in a hypothetical case, what we are trying to do is basically you take a 10 power 30 and a minus 10 power 30 and C is equal to 1. Okay. So now when you add A plus B, any floating point representation will directly say, okay, this is 0 and you add a 0 to 1 and that's all. Okay. Then you will go directly get a 1 as an answer. But if if you just repeat it, when you add B plus C, minus 10 power 30 and plus 1, the effective output is almost near to 1. Okay, since the way of representing floating points on a computer is different, you have a parts of exponent and a mantissa. The last one is often disregarded. When the last digit is disregarded, this always becomes equal to 1. Okay, so now when you go ahead and add these both, then the application will be answering will be 0. So now you see and understand the problem. So if you add a plus b and then a c to it, the answer is 1. But if you add b and c together and then you add it to a, then the answer is 0. Okay, so this is the classic non-associativity problem. This is what is creating you uh, in a LLM. This is exactly what creating you the non-deterministic and non-repeating behavior of the LLMs in practice. So this is the core reason, and we will discuss the indirect reasons that this contributes to also in this video. So let us see the floating point representation in a little detail. So whenever you take the floating point uh, data structures or see the data structures in the real world, you always have a sign bit and then a exponent and a fractional bit. Okay, so exponent is 10 power x or so and so, and then fractional bit. Now, in your LLMs, whenever you are inferencing, so what there are two phases in a LLM. Okay, you either train the model or you infer the model. That means your model is fixed and you give an input to the model or a whatever transformer or sequence to sequence, whatever model it is, and then you get the result. Okay, so the second part is called inference. Okay, so whenever you are inferring, all your operations that are happening are always happening in your floating point operations, and that is the reason GPUs are called flops. GPUs are measured in floating point operations per seconds, flops. Now, if you see various representations which we use inside the GPUs or inside the computers, they all have a limited length to represent your, you know, exponent component and a fractional component. Okay, anything does not fit in the fractional component always is disregarded. This we have studied in our first year, second year, third year of engineering. So this is almost at a acceptable level. But what is not acceptable is in a computations, we either do some mathematics, interest calculations and all, and then we round off the errors to two decimal points, nothing changes there. But when it comes to LLMs, you cannot round off, because the moment you are rounding off every other time, the same thing does not happen. So, so the result is changing by a very, very small bits. Okay. So now there are a sequence of multiplications that happens in the orders of hundreds. Sometimes several thousands multiplications will happen, matrix multiplications. So in a fractional component, even if there is a very small error that is there, it will blow up and create a non-associativity problem or the floating point rounding off errors. So if there are multiple stages in a model, that will generate the output, and the stage one uh, rounding off error will go and pass to the stage two. And that is the exact reason why floating points are the reason for your non-deterministic behavior in two ways. One, rounding off errors, not being non-consistent. The second way is the associativity problem. When it comes, your order gets changed, the operand order gets changed, so your result gets changed. So what it will force is, in order to get a deterministic results or the same repeatable results for LLM, the exact order of the operands must be the same. Okay, so now there are third player which is coming into that. What is the third player is? The third player is in order to get you the exact name, you also need to have the perfectly working floating points. You have to have the perfectly working associativity problem. Even if you solve these both, then the order of the calculations should not change or must not change. This is the third reason why your LLMs give you different results for every different run. We will see why, what are the methods and what are the reasons why the operands of the multiplications are also changing, because it's the same error or it's the same order. Why can't you multiply it in the same order? We will see in this video in the next section. Now, one reason why you cannot see or get the things in the same order again and again is because of the parallel computing that you will use for the inference. So let us suppose you are inferring a lot of requests. Okay, any GPU is a massively scaled, compute. So what happens is you cannot have a one GPU and a complete ecosystem for your inference request, isn't it? So when you cannot have an inference request just exclusively for you. Obviously, your request needs to be queued and batched with multiple other requests that are at that point in the system or inference system. So let us take an example of GPT-5 mini, or you can even take the GPT Gemini Flash. Okay, so at any given point of time, there will be several hundreds of people who are requesting the uh, output from the same model. Okay, when it is the output from the same model you are requesting, so you don't expect that this large model, one exclusive hardware is completely given to you. Okay, isn't it? So what they will do is all these sequence of words will be called batching. They arrange it in a separate input sequences, and then this model is will go ahead and predict you. So if you see, there will be models in the sequences or parts of the models that are run as part of the uh, you know inference sequence. In the inference sequence, whenever you are giving the input sequence, there are many layers and layers. So your input tokens will go through. So when you are passing these layers, or when you are passing these inputs through the layers, what will happen is there are intermediary sequences, intermediary results, and other results as well. Okay, or your typical tokens as well. So once they are given, the GPU hardware is very, very expensive and basically is supposed to be fully utilized, isn't it? So what they will do is the inference servers will batch the requests along with other requests also along with your sequence of tokens. So now when they are batching that, obviously not all the parts of your sequence will set into the same sequence. So then they will get juggled up and rearranged back. When they are getting rearranged back and juggled up, that is where you are getting the floating point associativity problem. Although they are semantically correct, their syntactically they will vary because of they will influence the logits part of it. So that is one reason which is contributing through the floating point associativity problem, where your order is modified to get this. That is just not the one reason. Okay, so although batching is one of the reason, sometimes data placement is also a reason. For example, you take a Qwen3 image or large images, 1 trillion parameter, 2 trillion parameter models. So E- all the parameters of the model will not fit in one GPU, isn't it? So what they will do, they means the inference servers will do is, see, whenever if you want to reload a model path onto a GPU, the IO operations are much more expensive than the inference operations. So trying to do one inference will cost you a lot in terms of time and the operations. than trying to do 10 consecutive inferences. For example, if you want to do load a model, model loading means copying all the biases and weights onto the GPU RAM or GPU memory, and then inferencing means use the GPU memory to manipulate the uh, input sequence tokens. So what they will do is they will divide the large models into GPU 1, GPU 2, GPU 3, GPU 4. They make a shards of the model sharding. So after that particular shard, they will route the input sequences of your input into those GPUs and come back or take the results back and reaccommodate and give you back the answers. So that is how any inferencing servers work, or optimized inference servers will work. Now, when they want to do this, it also depends on the co-load of your inference server, how your inference server is having a co-load. So for example, I asked a question about Apple, and you asked a question about apple juice. Okay, apple and apple juice are almost very near, because they are talking with the same thing, and most probably, I'm not saying exactly, most probably the same GPU will serve both the parts, because the vectors are very very same. Okay, but apple and apple juice are two different things, but the vectors are very very same. Okay, so if that is the scenario, and they both the request come at a given point of time, GPU 0 if it is serving, and because my apple request is there, my apple juice request will be sitting in next slot, and thereby there will be a very very small change in the output because of the associativity problem which is there, because the other tokens will come back in the same sequence, and this token may come back at a different order, and that will change the order, although semantically correct, because this you are filtering it multiple times, but the order change, since the order changed, your output slightly varies. This applies for text, this applies for images, this applies also for the videos. So you may try to do get reproducible results by putting the penalty tokens, but putting the repeat tokens count, or limiting the output context length and all. But nothing is going to change this ordering problem. So that is why this is the third indirect reason where your model inferencing will also influence the deterministic characters of your LLM. The next story runs around the scale of the parallelism. So now we know the order changes, isn't it? So as and when the parallelism increases, your determinism goes low and low and low and low. Because whenever there is parallel, you will have to split the tasks into multiple tasks, and you obviously have to run on multiple GPUs, and thereby your order goes down. So as the size of the model increases, your deterministic characteristics decrease. So if you are comparing a model that is running on a single GPU on a single machine with all same constant parameters, versus if you are running the same model on a multi-core, multi-GPU machine, your determination or determinism varies, or your repeatability varies because of the task splitting and inferencing. So this may not be, theoretically, intuitive, but it is reality. If you are parallelizing a task, then your determinism, when floating point calculations are included, always goes low. So this is also one of the contributing pattern, or one of the contributing problem for the deterministic characteristics of LLM. Now, one more reason why we are looking at is co-location of the other request similarly. So we just touched upon, but this is a diagram of it, where in which if you are putting out certain noise or the environment. So the output tokens that are going to come are being influenced by the same parallel load on that particular GPU at that particular given point of time. How we have seen, we have discussed in this video, but this is also a contributing factor to non-determinism. So if you really want to see how this does this split up the data, okay. So what you can do is, if you see sometimes, like I say, okay, I give a large context also. Okay, same repeatability on the large context request of LLM. So there, what happens is, if the model is small but multiple GPUs are running, so even then there is a deterministic problem, because the way you split up the data and give it for the inference. Because when you split up the data, several workers receive the same identical copy. But then when you are calculating and redistributing the weights and aggregate weights between these, then your order might change, and that is the reason your deterministic behavior is also impacted. And sometimes even the libraries you use is also impacting the deterministic outputs. Okay, because if you are doing a static batching like in Hugging Face pipelines or NVIDIA's transformers, then your responses are slow, but your outputs are more consistent. But if you are using text generation interface or VLLMs, Quan models are typically VLLM based. If you are using them in any case, due to the continuous batching mechanism, you will uh, face the variability in the outputs. So that is how your variability gets impacted. So if you are going for the more and more efficient GPU utilization or GPU utilization models, then your variation of the outputs is going to be seen. Okay. So now, coming back to the original paper talks about certain problems that could be handled deterministically. But if you see all these issues, what determinism means is, it means lower GPU utilization on a normal circumstances, a heterogeneous or homogeneous infrastructure, because how the floating points are represented, and sometimes even the CPU architecture as well, or GPU architecture also. GPU architecture also manages, or GPU architecture also contributes to this kind of a non-repeatable results. So here is a small, very small thing on what kind of a performance input or performance data that is already there. So what typically happens is, if you are looking at data and if you are giving larger context, okay. So if your measurement is this at the same size of it, and if your input text is the same and all, then it doesn't matter. But if you are like sending more and more tokens in the inference request, as and when the tokens inference is request, or number of the tokens in the inference request is increasing, you will see more and more and more variability in the answers. So longer the question, longer the prompt, more variability. So if your prompt length, although you can say technically the prompt is the same, should be the same, but if your prompt length also will generate a different answer. So, like one additional spacing or one additional special character also will impact that. But this graphic is to only tell you what are the time variances, which when your length of the tokens, output length of the token also varies. So this is what is this. So you can improve when you want to generate smaller length of a tokens, and it takes a lot of time when you want to have a long length of a responses as well. So although this is not a direct contributor, this also contributes to your variability. because when you are giving inputs can be variable. Although you are giving the same input questions, the input inferences can change. For example, what is the cricket score or what is the weather? Okay, so your prompt is the same, but the inputs are changing. So therefore, the output also may change. Just not just the parameter, but also other things. So the even the length of the prompt tokens also contribute very little to the non-repeatability nature of the LLMs. Okay, we discussed a lot on the GPUs, but what's about the multi-core CPU problems? So, if it is a problem with the GPUs, what about the CPUs? Why multi-core CPUs also show the same scenario? Even on the multi-core CPUs, whenever there is a parallel computing, okay, the order of the thread execution is not in the control of the user, and not every time your sequence tokens are readjusted or split and come back into the same output. So whenever there is a non-associativity which is involved there, even the small differences are there, it will impact the logits. And whenever the logits are coming, you can get a different results. Okay, so that is why these are very, very specific to CPUs also, GPUs also. Unless we fix the floating point associativity problem, we will not be able to get the deterministic outputs at this point of time. So that is the major challenge as on date. So now coming to the most controversial, question of the day: does model itself influence the deterministic characteristic of a LLM inference? I say and stay on the line of yes, model impacts. Because let's take an example of mixture of experts. In the mixture of experts, what will happen is based on the input sequence of lengths, you will pick up certain experts, okay, in the within the model, and those experts will infer the data. Okay. So now, as the time changes, based on the feedback, router may not always pick up the same expert for the same given input sequences. So some models work this way. If you see the just go ahead and understand the mixture of expert model and see the transparent routing. Okay, so I have tried it on K2 yesterday, or released last week. There you can see which exact submodel it is invoking of the mixer of experts. So if you are looking at mixer of experts model, they are expert in rerouting to the pieces and parts whenever the inferences change. Even if the prompt are same, sometimes in a random order it will pick the expert. Okay, due to various weights feedback mechanism. So there is models also, the model architecture also will influence the determinism, is my standpoint at this point. There are many references which are pointing to that also, but technically speaking, model by itself should not influence the non-deterministic character, but we are not in the ideal world to do that. So models are also a contributor to non-determinism. Okay, coming to the end of the video, this video did not talk about the solutions to the non-deterministic behavior of LLMs. So we are inspired by the Thinking Machines blog, and I just wanted to put out what are the factors that are contributing to the non-deterministic behavior, and here are they. In future, there may be a scenario where we need deterministic algorithms and we need deterministic hardware for generating LLM inferences. When I say LLM inferences, it could be audio, it could be video, it could be image. Okay, but we need that, and I think there are efforts going towards that. But the general public is differed on why we should do it. Okay, if you see, uh, what are what happens if we have a deterministic LLM? They are more reliable. People who are responsible AI vigilantes will be more happy, and your prompt can be much more optimized. Okay, you get the better reproducibility in the outputs, and you get the consistent outputs. But at what cost? Okay, definitely there is a trade-off. Okay, so you cannot have a creativity and repeatability in the same place. So that is one. And second thing is, you may not get the so diverse outputs which we are getting. Okay, and then it definitely comes at a higher computational cost, also higher infrastructure cost, because all your hardware needs to be patching aware, that means the sequence aware, and your hardware may be precision aware as well. So, and the algorithms are also may need to change. So these all come up at a trade-off. But at what cost they will come up at a trade-off? We don't know at this point of time, because community is checking on it. Okay, so there may be some scenarios where the deterministic LLMs are a mandate, but I don't think at this point of time broader community is hell bent on it. There are groups who are okay with non-determinism as well, but let us see what will be the future, and we will see how these shortcomings or these kinds of wide variety problems are addressed, keeping in view of the thoughts or commercial off the shelf or a consumer kind of a hardware requirements in mind. Thank you. Thank you for staying with us, guys. I think this has been a long video. I hope you enjoyed the video. I hope the concepts of non-determinism are very, very clear at this point of time. Do like and subscribe to Medo Yantra. We will ensure complicated concepts like this are simplified as much as possible for you. Also, there is a Telugu version of this video that is scheduled to release on Thursday, the 18th of September 2025. So, if you are Telugu native speaker, please do check out that video as well. Thank you. Thank you, guys.